All right, I think we've hit Berkeley time. We should get started.
Mhm.
So thanks everyone for coming. I think this is the last Compass lecture of the semester. And we're really excited to have Felipe Gonzalez here with us. Felipe is a Chilean physicist who studies matter in extreme conditions. And in his PhD, Felipe used condensed matter techniques to address a bunch of interesting questions about whether Jupiter's core can be dissolved by metallic hydrogen and also about the stability of iron at the center of our own planet. And then after completing his PhD in physics in 2015 at the Universidad de Chile, he worked for the Chilean Nuclear Energy Center, where he looked at material damage by deuterium irradiation using atomistic simulations. And then in 2016, Felipe joined the group of Burkhard Militzer in the Earth and Planetary Science Department here in Berkeley, and he currently works there as a postdoc researcher. One fun fact about Felipe is that he's attended almost every possible metal concert in the Bay Area, and you can check out his record of that on his website. And in his research, he continues to study materials in extreme conditions, and he'll tell us more about that today. So take it away, Felipe.
Okay, thank you very much for that kind introduction and for the opportunity to allow me to present my research, which is related to this exciting world of studying materials in extreme conditions. And today I want to tell you how this is related to the interior of exoplanets and to nuclear fusion. And I am a postdoc, as you said, in the Earth and Planetary Science Department in the group of Burkhard Militzer. And we're interested in studying what happens with minerals and materials at different extreme conditions like the ones you see in the background. For example, in planetary condition events where high pressures and temperatures can be generated, or at the interior of Jupiter, Saturn, and other planets, where you also have these extreme conditions. So I obtained my PhD in physics in Chile, and my background is condensed matter, but I came to Berkeley to study planetary science. So you may wonder how that happened. And you know that Berkeley has been a cradle of great discoveries over the years. We even have an element in the periodic table. And there are also other institutions where great science has been done over the years, in particular the Livermore National Lab, and they also have an element in the periodic table. And these elements are actually what tell us what the universe is made of. The combination of different elements make compounds, and these compounds can be at different conditions, but due to obvious reasons, we've only studied them at ambient pressure, that is 1 atmosphere. And we don't really know, we have very little knowledge what happens with them when you expose them to great pressures. And that is what planets are made of, materials at extreme conditions, and that's what I'm interested in. So there are currently experiments being done to achieve these conditions, and one of them is the National Ignition Facility in Livermore, where they have taken this endeavor of trying to explore this strange regime of matter, where you have such high temperatures of billions of Kelvin and pressures of billions of atmosphere, where we don't really know how matter behaves. And it's important to explore it in order to understand it again, because those are the conditions where you would find the Jupiter's core, white dwarf cores, and a series of other planetary interior conditions. So it is important not only for planetary science, but also for nuclear fusion with this inertial confinement technique that NIF uses, because they have actually to take matter from ambient conditions all the way up to the conditions, extreme conditions necessary for ignition in nuclear fusion, which are like billions of Kelvin in temperature at very high densities. So they try to reach that with lasers, very powerful lasers. I will talk more about it in a minute. And this establishes a very deep link between extreme conditions and planetary interiors, because once again, those are the natural laboratories where you will find these conditions, and it's important to understand matter at these conditions if you want to understand how planets form and evolve. So there are many labs trying to take the experiments and expose matter at these extreme pressures and try to observe new phases of matter. And one of the latest experiments very recently is that one of them took polystyrene, which is just a plastic, and they put it at such extreme conditions that they formed diamond. Can you imagine that? They took normal plastic and they converted it into diamond. And the reason why that happened is because the conditions were so extreme that the bonds between carbon and hydrogen broke, and the carbon left behind was at such extreme pressures that it formed diamond. And they have evidence of that uh, due to the X-ray diffraction that has been performed in these experiments. So this is important not only for material science and a proof of concept that we are understanding the physics behind this, but also because it has consequences for planetary science. So now we think that, for example, diamonds are raining in Neptune. And we think this because Neptune's composition is very similar to polystyrene. At least there's a lot of hydrocarbons there in Neptune, and they have a chemical composition that is similar to plastics, and the pressures and temperatures are equivalent to those that we found in the experiments. So if the conditions are the same and the material are the same, we think that nanodiamonds can be formed in Neptune's interior, and they can fall down due to gravity. So that's how we think that the diamonds are raining in Neptune. And you see already that there are a series of phenomena that can be occurring that we'd have never thought of if we hadn't understood the material science behind this. So I want to tell you a little bit about planetary science and what is the current status of exoplanets. And then I will talk about shock waves and experiments and simulations done to achieve these conditions. And in the second part of my talk, I will talk about two particular projects where I've been involved, which has to do with the Jupiter's core, how the Jupiter core is being dissolved, and the crystallizations of super Earth cores. So in terms of exoplanetary science, you have to know that it's a relatively new field. It has only about 20 years, and it is possible due to the missions that have been put in space, in particular Kepler, that has been one of the main ones, and that are able to observe when a planet eclipses its own host star, decreases the brightness a little bit. And astronomers have been able to achieve this with incredible precision that allows them to measure the radius of the planet, but also the atmospheric composition, which is amazing. And there's another technique called the radial velocity method, where the wobbling of the star is related to the Doppler shift of the spectral lines, and that allows you to measure the mass of the planet. So with mass and radius, you already have an idea of the density of the planet. And this field, as I was saying, resulted in the Nobel Prize of Michael Mayer and Dieter Keller for the discovery of the first exoplanet in 1995, which is relatively recent. So there's a lot to know about this field and tons of projects to be done in order to understand better what planets are made of. So we have already discovered more than 4,000 exoplanets, planets orbiting other stars that we think are all sorts of categories for these planets. For example, lava worlds that are so close to this host star that they can be entirely molten, rocky planets, maybe ocean worlds, hot Jupiters. And here's where it comes the material science, because we have to understand what happens with the possible materials that they are made of in order to provide better constraints for their formation and evolution. So if you look at the statistics, it seems that at least 1 in 6 stars has an Earth-sized exoplanet, and they seem to come in two different populations. So they're super Earth and sub-Neptunes that we don't have in our solar system. So why is it that these two types of planets are so popular out there and we don't have any in our solar system? How they form, how do they get there, what is their equilibrium state, and so on. So that already prompts a lot of questions. And part of it is understanding, once again, what happens with the materials that they are made of. So we try basically to study candidate materials for the composition of these planets, at extreme pressures and temperatures and see what happens with them and what the implications could be for the formation of these planets. And this is how we've learned, for example, that normal water, H2O, has a metallic phase at high pressures. It becomes a metal. And there's also super ionic phases of water where the oxygens in the lattice are still vibrating like a solid, but all the hydrogens start flowing like a liquid in this oxygen matrix. So it's a state of matter that we don't have currently in our ambient pressure conditions. So we've also learned that silicates, for example, MgSiO3, which is one of the major compounds that made up the Earth, can be electrical conductors in liquid state at high pressures. So that means that if these super Earths are kind of Earth-like composition and they have a liquid mantle made of these silicates, they are probably generating magnetic field from their mantles, which is something that you will never see in the planets of our solar system. So behind all this is the techniques we use called ab initio molecular dynamics, which is basically solving the complicated Schrodinger equations of quantum mechanics with supercomputers. So you may wonder, how do we know the interior conditions of exoplanets? So one of the ways of doing it is doing models using materials. And I think you're all undergraduates in physics. You can follow like a few equations here, and they are relatively simple. So the mass enclosed in a shell of is given by the density and the volume. So that leads to a differential equation for the mass as a function of distance from the center that is related to the density. Then you have hydrostatic equilibrium, where the pressure changes as you go deep down into the planet. And that leads to a differential equation for the pressure that depends on the mass enclosed in a shell of mass m and the density. And then you have to have an equation of state to solve this system. And here's where material science comes to save the day, because you need to understand how the materials behave at these pressures in order to solve these equations that tell us about the interior. So we have to generate this equation of state, just to put them here and obtain, for example, an interior pressure profile for the planet. So you suggest a composition for the planet and solve these equations, and you obtain, as a result, how the pressure changes as you go deep down into the planet. And for example, for a planet like Earth, you have that at the very interior, you reach around 300 gigapascals, which is around 3 million times the pressure in the atmosphere, our ambient pressure. But if you consider a planet that is 10 times the mass of the Earth, then the pressure at the interior can reach up to 60 million times the atmospheric pressures. So you already wonder what is happening with all the materials that are inside these planets, that are pressures that are not present, not even in the core of the Earth. So solving these equations, you can obtain mass radius relationships for exoplanets, where you can obtain, for example, what is the mass that an iron planet will have. For example, if the planet was entirely made up of iron and it had 5 Earth masses, then it would have this radius, which is a little bit about the radius of the Earth, which means that it will be very compact and very dense. But if for the same mass the planet was made of just water ice, and if you imagine that, then the planet would have a much larger radius because the density will be smaller. And you can do so for several compositions. And on top of that, you put the measurements, what astronomers have measured for exoplanets. So they can measure, as I said, the radius and the mass of exoplanets. And when you put them in this diagram, you can already see some features, right? You can see that this planet, Kepler 11b, for example, could be compatible with a water composition, so could be an ocean planet, while this one are more closer to a silicate type of planet. There seems to be planets out there that could be made of carbon silicates, silicon carbides. And these implies that these type of composition could have, these type of planets could have a diamond layer inside. So it's really exciting that the possibilities for the compositions that an exoplanet can have. And again, the material science, it's important to know what the possible compositions can be. So in terms of simulations and experiments that can be done to reach these conditions, we have shock waves. And the shock waves are basically what you were seeing in the background here, a very violent event where a lot of energy is generated, like in the event that formed the moon, for example, when a large object impacts an object that is the size of the Earth, then you generate very energetic collisions that reach very high pressures and temperatures, and you generate phase transitions. For example, the material can evaporate, can go into different solid phase transitions, and it can melt. And it's important, again, to understand what happens with minerals that form these objects to understand this process better. So the idea is to generate these shock waves, these violent collisions in the lab. And if you remember the unfortunate events in Beirut last year, where you saw like this like factory exploding, it generated this blast. And this blast is basically a shock wave. And this shock wave generates new states of matter behind it, where matter is compressed at higher densities and higher pressures and also higher temperatures. So that's a way that we have to access these new states of matter. And the collection of all these new states of matter in shock events, we call them the hugonio curve of a material. So there are several labs where this has been done. For example, in UC Davis, they have a gas gun where they literally throw a bullet into a target and they generate this impact and obtain these new states of matter. You have this Z machine in Sandia Lab where they can generate extreme magnetic fields. And with those fields, they can accelerate flyer plate that impacts a material and generates the shock wave. And you also have laser compression. And here's where Livermore comes, because in laser compression, you can actually use lasers to generate this shock wave. And that's what NIF is doing. They generate a very intense laser pulse that arrives to a material and generates a shock wave into this target. And you can see in the size of people here compared to the chamber here, each of these windows here is a window where a very powerful laser enters, and it's like around 200 lasers entering at the same time to generate this very energetic laser pulse that will generate a shock wave. And the impact will hit a very small chamber that is like this size, and in the center you have a very small capsule, like millimeter size, which has deuterium and tritium. And the idea is to compress it to extreme pressures and temperatures that are necessary to generate ignition and finally nuclear fusion. But we're not there yet. We have not generated ignition, but we can meanwhile use these lasers to compress matter at these extreme conditions that we need to understand the interior of planets. So when you generate a shock wave, we actually have physics behind this that allows us to understand these states better. We have conservation equations that allows us to understand what happens with the matter after it's been shock compressed. And we put these states in a line of shock velocity versus particle velocity, again, which is called the hugonio. But using the physics behind these processes, we can convert this into pressure and density and generate this from simulations. So we can generate actually the hugonio curve from simulations and predict what an experiment will observe when doing these shock compressions. So we do so by simplifying this equation into a more simple energy equation that we can solve once we perform simulations of matter at extreme conditions. So the way we do it is we basically take a material, we simulate it at different temperatures and densities, and we try to solve this equation to try to find which states satisfy these equations. And if we find these states, we're basically finding one point in the hugonio curve. So to do so, we use density functional theory molecular dynamics that is a technique in quantum mechanics, and also path integral Monte Carlo. In DFT, we have Schrodinger-like equations where electrons are waves, wave functions. And in path integral, the electrons are literally paths that you have to integrate over all possible paths. And that gives us a description of the material itself. So when we obtain this hugonio curve and we compare it to experiments, we have observed already that we have a beautiful agreement between the experiments, which are these points with error bars, and the curve that we predict from our simulations. So this means that we are able to predict correctly what the properties of matter will be at these extreme conditions, because we have confirmation from the experiment. We've also can deduce some very interesting thermodynamic properties like the specific heat. And we see some features here that are not accessible in normal conditions. For example, this peak here means that the oxygen atoms in the most inner electron shell, the 1s electron shell, is being ionized by temperature at this 1,000,000 kelvins of temperature, while the second peak here for MgSio3 corresponds to the ionization of the innermost electron shells of magnesium and silicon. And if you increase the temperature even more, then you come to a limit where you just have an ideal gas of positive nuclei and negative electrons all going around in a fully ionized plasma. So it's very nice to see how the thermodynamic properties evolve as a function of temperature. So we can do all sorts of diagnose for matter at these extreme conditions and calculate, for example, this radial distribution function, where these peaks basically tell us the average bond length, like what is the separation between different types of atoms. And you can see that they are different at different pressures, different densities, and different temperatures. When we did it for magnesium oxide, which is also a very relevant material for planetary science, we also see a very nice agreement between the available experiments at these extreme conditions and our predicted hugonio curve here in black. So this is very encouraging because it seems that we're doing very well. So we have studied like all sorts of material in this warm dense matter regime. And it's important, once again, to understand exoplanetary interiors, also the neutron stellar atmosphere, white dwarf cores, and also for studying what would happen in an inertial confinement fusion experiment. And we have recently published a paper where we provide all the equations of state that we have found in this regime, and also a code called first principle EOS, where you can download it and combine this different equation of state in what's called the linear mixing approximation. And that allows you to create new equations of state for materials that we have not explored. So that's pretty cool. Okay, so now in this second part of the talk, I will talk about these two projects that I mentioned. And the first one of them is how's the Jupiter's core dissolving, why we think this is happening. And in order to understand this, you have to put it into context. And if you look at the theory of planetary formation, you will see that accretion is one of the main processes that we think is forming planets, and it's a very complicated process where dust start agglomerating due to electrical forces. Then it forms pebbles that gather together as rocks. And it's a very, very complex process. But in the end, you end up with a very large object made up of very varied composition of minerals. And these minerals will be at very, very high temperature in the beginning because the temperatures increase as energy is delivered into the system. And if you see the assembly line of planets, if you consider that you have not enough mass, like a very small mass to start with, then you're not able to accrete many gases around you. So you end up with a very tiny atmosphere. But you start with a very large mass, then you can accrete a very large atmosphere of gases and end up like Jupiter. But the thing is that as you add more and more gas, the gas gets pressurized due to the layers that are above, and they form this phase called liquid metallic hydrogen, which we think is the responsible for the magnetic field of Jupiter. And it's a phase of matter that we don't have on Earth because it only forms at very high pressures. So we wonder, is it possible that liquid metallic hydrogen acts as a solvent of the rocks that accreted the planet? So this is the question that we wanted to address. So we have to consider the chemistry between liquid hydrogen and, the possible rock composition, and answer the question, can a liquid metallic hydrogen dissolve the rocky core? So we have to consider that the conditions that are in the Jupiter's core are around 4,000 gigapascals, which is around 40 million times the atmospheric pressure. And temperatures are around 15,000 or 20,000 Kelvin there. So there's no experiments, no chemical models that allows us to predict how this interaction will take place. And again, we have to consider possible compositions, but we obtain that from evidence that comes from space. We receive thousands and thousands of meteorites that fall into the Earth, and they are evidence of the materials that are out there forming planets. So one of them is silica, which we think is a major constituent of the planetary interiors. So we consider, is it possible that silica is being dissolved by metallic hydrogen? So we want to understand this chemical reaction. And the way we do it is calculating the Gibbs free energy of solvation, which is basically trying to see whether the Gibbs free energy of the dissolved state here is smaller than the Gibbs free energy of the state that is not dissolved. So it's an energy balance argument. So if this term delta G is less than 0, then the system will dissolve at the pressure and temperatures where we explore it. So that is what we did, and this is what we obtained. So for the pressures and temperatures that we believe that Jupiter's core is, in particular the core mantle boundary here, and also Saturn's core mantle boundary, we find that this system is dissolved. That means the energy of the dissolved state is smaller than the energy of the undissolved state for any composition, for any concentration that you choose. And we did it not only for silica, but also for other minerals like MgO, ice, and iron. So we think that liquid metallic hydrogen is a very good solvent of any rock that you put there. So we now have, we think that metallic hydrogen is dissolving in Jupiter's core, but how do we know if this can actually be happening? And it turns out that there's a mission out there called the Juno mission that is orbiting Jupiter and measuring the magnetic field and gravity field to an unprecedented precision. And they're measuring what's called the gravitational moments here, which is nothing but the integral over the density profile of the planet. So if we measure these gravitational moments, it can tell us about what the possible density profiles are at the interior of the planet. And the most recent studies indicate that the measured gravitational moments can be explained if you assume a profile that does not sharply ends in a solid core, but considers a core that is diluted. That is, a diluted core profile, density profile, is compatible with the measured gravitational moments. So that's an indirect evidence that we have that the Jupiter core is dissolving. And this is really exciting. So it means that we are in the right track with our simulations. And finally, I want to tell you about another project that I've been involved, which deals with super Earths, these massive kind of rocky exoplanets between 1 and 10 Earth masses that are not present in our solar system. We don't have super Earths in our solar system, but it seems to be a lot of them out there. So what we want to calculate here is melting curves, and in particular, the melting curve of iron. And the way we do it is with these Gibbs free energy calculations once again. And from thermodynamics, we know that the melting point is defined as the point where the liquid has the same Gibbs free energy as the solid. That determines the melting temperature at a given pressure. There are other techniques there where, for example, you can put the solid in front of the liquid and determine the melting temperature. Other methods like the Z method, when you just literally heat it up until it melts. But in this case, we chose Gibbs free energy calculations. And we have used several methods in the past, like this Z method, to calculate silica, for example, once again, this mineral that is important for planetary science, and found that silica is solid at the conditions of the core metal boundary of Saturn and Jupiter, and also solid for this interior of super Earths. And experiments have validated this melting curve. And they also found that the liquid that you obtain when you melt silica is conducting. And remember, other simulations that we've performed indicate also that other silicates are also electrical conductors. So it adds up to this idea that super Earths could be generating magnetic fields from the mantle because they become electrical conductors. So in this case, where we are studying iron, again, we are doing this free energy calculations to study the melting curve of iron at high pressures. And we consider this stage where the planet has differentiated. That means all the iron sinks down to the core, to the center of the planet. And due to this formation process, it starts in a molten state. So everything is molten, iron is at the center. So it is interesting to understand how pure iron behaves as it cools down. So we also were able to calculate isentropes, that is constant entropy lines, because this is important for any planetary process where you have convection. Convection is directly related to isentropes or adiabats, because that's when a process is convecting, it's associated with an adiabatic profile. So that you will find in most models of adiabatic of convecting mantles and cores. So if an adiabat in the pressure temperature diagram looks like this and intersects the melting line with a shallower slope, it will mean that the core of the planet will start growing from the center. But if the adiabat has a higher slope, then it means that the crystallization of the core will start from top to bottom. So that already will tell us about a formation scenario. And that is what we did with iron. We calculated these isentropes and the melting line, which is here. And the first thing we find is that we are in the first case, where we have a shallower slope. So the crystallization of super Earths should start from the center, as it happened with the Earth. And the second thing we found is that the melting curve is way above like extrapolations from previous predictions, which means that iron is much harder to melt than previously thought. And if it is harder to melt at the interiors of super Earths, then crystallization is more favorable. It will be harder to have an outer core like in the Earth. So this melting line is above the core metal boundary conditions of Jupiter, Saturn, and also about models that have been done for super Earth of 10 Earth masses. So another thing we learned is that doing this formation, these interior models that I told you about, is that if you consider, for example, a 5 Earth masses super Earth that has a silicon mantle, it will already start crystallizing when the temperature drops down to 13,000 Kelvin, which is already really high. So crystallization will start from the center, and by the time it reaches 12,600 Kelvin, it will be entirely frozen. And that is really important because if you look at the models that suggest which temperatures you could have at the interior, they will never suggest such high temperatures. So it means if the temperatures at the interior of a super Earth are below the temperature that is necessary to crystallize the entire core, it means that super Earths have frozen cores. They cannot produce an outer core that is liquid like we have on the Earth because the pressure is so high in these planets that it crystallizes iron at the center. So if this happens, it means that we won't have this interaction between an inner core and outer core that through convection, they generate a magnetic field. So it is possible that super Earths cannot have a geodynamo that generates a magnetic field. But remember, they can still generate magnetic fields from their mantle using the silicate liquids. We've also learned then that the silica should be solid at the interior of super Earths and gas giants, and that there is erosion of the core of gas giants. So with that, I want to leave with two takeaway messages. And we have learned that experiments and simulations can tell us about new phases of matter, and we can use this information to produce phase diagrams, study melting curves and properties of matter that can constrain the models to study planetary interiors. So doing so, we learn more about their formation and evolution, and we also learn about new physics. So with that, I would like to thank you and would be happy to answer any question you have.
Awesome. Thank you for the great talk, Felipe. Super cool pictures and really cool videos. I think we have some time for questions.
Would there be a difference in magnetic field based on where the liquid part is? Like for us, um, we have a liquid inner core, um, sorry, outer core. That's where we generate our and liquid mantle. That's where we generate our magnetic field because of iron. But would like having a different material like silicon dioxide make a difference in the kind of
Actually, yeah, actually, that is what has been suggested by these experiments and simulations. Since there's a lot of silicates around in space, we think they're very likely to make the mantle of super Earths, but the temperature will be high enough, we think, that they can be molten. But in these molten states, these silicates like MgO, MgSio3, silica, in the molten state, they can convect, and that convection could generate the magnetic field in these planets. That doesn't happen in the Earth because in the Earth, we don't have such extreme conditions to generate this electrical conductive phase. Um, and in the case of the Earth, we generated with this outer core of iron that has some alloys like nickel, we think, and that through convection, they generate the intense magnetic field that we have. But we think that in the Earth is mostly iron. There's just a little bit of other elements to make that alloy. Again, nickel, could be sulfur, but I don't think that considering just, for example, pure silicon would be a viable um, option because you would have to justify it with models. It is not very likely that the silicon will stay by itself. But yeah, silica, for example, silicon oxide is a very likely candidate to be a material of a super Earth's mantle.
Okay.
Any other questions?
Other questions? I have a question while people are thinking. So when you're modeling, like, I guess how the core of Jupiter is dissolving, can you take it further and keep propagating the dynamics? Like, will it get to a point where it's totally liquefied, but then the pressure will solidify parts of it again and it will kind of oscillate back and forth? Or how does it keep evolving after it liquefies?
Yeah, that is a great question. And there are actually different like teams, or if you want, like layers of study of these type of processes. And doing what you mentioned is basically running a hydrodynamics code that uses the equations of state of materials to actually simulate the dynamics and how this could evolve in time. In our simulation, in my simulations, I have no idea how long it will take to dissolve the core, because that's not included in the thermodynamics. We just know that it's a preferred state. But you can actually do that. And I don't know if any group has taken like that project, but this measurements of Jupiter's gravitational moment indicate that there should still be a core over there. I mean, the density increases in such a way that there should still be an identified core, not completely diluted. That's what measurements show currently.
Interesting.
I had a question about the cores cooling down. If you could just kind of like re-explain that. So in super Earth, the pressure is so high that the core will actually begin to freeze. Is that kind of the idea?
Yeah, actually, you got it right. Let me go back to that slide. So if we consider a very basic model for a super Earth with just a silicate mantle and iron, pure iron in the center, then you have to have a model to predict what the pressures would be here, right? So we're talking here about pressures of 2000 gigapascals. And then the natural question is, does iron freeze? At what temperature iron freezes for 2000 gigapascals? And then the core mantle boundary here would be at a lower pressure, say 1000 GPa. And then at what pressure, at what temperature does iron freeze for 1000 GPa? So here we basically predict that if the the lowest melting temperature would be 12,000 Kelvin, 12,600, for the conditions of the core. At the lowest pressure, this would be the melting temperature. So if you have an average temperature that is below that, like the model suggests, some models suggest 6,000 Kelvin, then no part of the core has a temperature that's higher than the melting temperature of iron. So all the possible pressures that you will find there have melting temperatures that are above what any model would suggest. It is still possible that these temperatures can be so high, but actually constraining the temperature inside an exoplanet is very, very difficult. So currently, from what we know, is that temperatures would never reach such high values. So for all the pressures that you would find in a 5 Earth masses exoplanet, super Earth, you will not have temperatures that are compatible with liquid iron. That is the argument. So then you won't be able to generate an outer core that is liquid and convection cells that generate magnetic fields from the core.
Wow, that's really interesting. Thanks. And that was going to be my follow-up, is the ultimate consequence of that is the outer core, right, in the magnetic. Thanks.
Sure.
I had a really out there question.
Sure.
So I'm also a condensed matter person. And I was wondering if there's been any thought or is there any possibility of finding some sort of superconductor in these really high pressure environments?
That is also a very interesting question. And I think that would be really hard because if you look at the superconductors that we have found, like the highest temperature superconductors are not even at ambient temperatures, right? So the superconductors are generally formed from very complicated compositions that consider lanthanides and very heavy materials of a composition, very special composition that allows superconductivity to take place. And it also occurs when the material is crystalline and at very low temperatures. So I am not aware of any simple composition that presents superconductivity other than lithium, for example. There are some phases of lithium that people think that are superconductive phase, but again, at high pressures but low temperatures. And when in a planet you go down, the pressure increases, but also the temperature increases. So that not only erases superconductivity if you have there, but it can also erase, for example, magnetic phases, because you would easily overcome the Curie temperature, and you could like erase the magnetic phase of a permanent magnet. Like what happens with iron, for example. Iron is magnetic at ambient conditions, but at high pressures, it has this HCP phase, which is not magnetic.
Mm-hmm. I think I was thinking about the carbonaceous sulfur hydride.
Okay. Yeah,
but,
I'm not really sure about which superconductors you can have with silicon carbides. And that's like a composition that we think could be likely due to the composition of some stars that are rich in carbon. So we think that the planets around could be rich in carbon. So that's why it has been suggested that they could be planets made of these silicon carbides. But yeah, it's an interesting possibility.
Thanks. And thanks for the talk.
No problem. My pleasure.
Just a quick question. If there's time, I wanted to follow up on that. Hi, Felipe.
Sure. Hi, Gene.
Hi. Following up on that question about conductivities, although superconductivity may not be very likely in the interiors of planets, there is still an electrical conductivity, and it may be still high enough, right? For example, ideal MHD to be valid. Is that true? You can calculate electrical conductivities, right, for these materials, and they may be high enough that nice things like flux freezing and dynamos can operate.
Yeah, you're totally right, and that's basically one of the studies that I showed you in the beginning. This one here, let me see. This one here was done in our group by Francois Soubiran and Burkhard Militzer, where we can basically calculate the electrical conductivity. So it's not superconductivity, just normal electrical conductivity, and calculate what's called the Reynolds magnetic number in order to have an estimate of how much magnetic field you can generate in a convective layer where you have this conductive material. So yeah, that is a possibility, and that's one way to address it, which is really interesting.
What are the magnetic Reynolds numbers?
I'm actually, I did not participate in this study, and I just know that it's a way of estimating the strength of the magnetic field when you have the viscosity of the material and the electrical conductivity.
Right.
So yeah, it's a way of making a plausible calculation of how strong the magnetic field would be in a formation where you have certain viscosity and electrical conductivity in a conducting fluid.
Okay, thank you.
Sure, no problem.
Sarah, did you want to ask your question?
Yeah, I have a question about magnetic fields. do we have a way to observe exoplanetary magnetic fields? Like, why should we care about whether or not you can make a dynamo or not in an exoplanet?
Right. That's also a very good question. And well, I would start by the second one. It's like, why do we care? Right? We'll never go there. Probably it's impossible to land there. These planets are so far. But we, as scientists, want to learn more about how these planets are formed and how they evolve, just out of curiosity, because that entire process of exploring how they can form and evolve can lead to can open the door to new questions and new answers that we might never even be looking for. So it just develops science better. And how do we observe magnetic fields in exoplanets? I think Eugene would be more a better candidate to answer that question, but I don't think it's possible. I don't want to say it will be ever possible, but I imagine that one way of addressing it would be just to observe some processes around that planet where trajectories of some particles that can be detected are deflected by that magnetic field. But I don't know if that's possible. I mean, these planets are so far away that we can barely capture the light of a star. I don't know if there's any particle that we can capture to observe like their trajectory like we do on Earth. That's how we probe our magnetic field. But I think it's important to study just for the sake of science, of doing great science and discovering new things that can open the door to new questions.
People are certainly trying to measure magnetic fields for exoplanets. As Felipe says, it is very difficult and it hasn't quite been done to anyone's satisfaction. But you know, there are a couple ways that people are trying right now. One is to try to detect aurorae. You know, emission lines from oxygen or nitrogen, which are excited as stellar wind particles follow magnetic field lines and slam into the atmosphere of the planet. So people are trying to detect, without success so far, auroral emission lines, so these nice greens and blues and reds. And the other way is to look for radio emission. So again, stellar wind particles will gyrate around, they're charged particles, and they'll gyrate around the planetary magnetic field lines and generate cyclotron radiation, typically at radio wavelengths. So people have tried to detect that. Our detectors right now, we just don't have enough collecting area to do it. But the next generation radio arrays, this is going to be one of the prime science targets, to try to detect cyclotron emission and measure. And once you get the frequency, right? Once you get the cyclotron frequency, then you've got a B field measurement.
Right. I was not aware of that. Thank you, Eugene.
Do we have time for one more question?
So I have a question. Would you mind answering, Felipe?
Of course, no problem.
Okay. So you mentioned, yeah, so we calculate a lot of the phase diagrams, right, in the deep interior. So the general question is generally how valid it is to describe the distribution of minerals. So are they all equilibrium, in thermodynamic equilibrium with each other, or should we consider some kinetic effect?
Well, that is also a great question. And you have to consider that in geological time state, in geological times, the materials have a lot of time to equilibrate into equilibrium states. So unless you're talking about, I don't know, if you imagine like I don't know, a scenario where something is happening out of the equilibrium, like some chemical reaction taking place in short times, we think that in general, like any layer would be in equilibrium. And if you want to defy that assumption, then you have to provide evidence of whether that's true or not. And regarding what you said, the kinetic effects, well, we study the phase diagrams of elements because we think that since those are states of equilibrium, the phase diagrams represent thermodynamical equilibrium states. So that's why they are so important. So you would have to consider a very particular process that you want to describe if you want to describe kinetic effects that are taking place out of equilibrium. So it depends what you want to study. Yeah, I would say that it depends what your question is.
But some review, for example, one old review by Raymond, he claimed that maybe the time scale is not enough to reach equilibrium if the convection pattern sometimes will not render the fully equilibrium. Maybe. Yeah.
Right, but you have to consider that Earth is the planet we know more about. We know
most. Yeah. Okay.
Yeah. So we know so little about super Earths that we are starting with these like baby steps, doing the most basic assumptions to start complicating the models later on when we learn more about them.
All right, let's give Felipe another round of applause for a really great talk. Thanks.
Have a great weekend, everyone. Thanks for coming.
Yeah, great talk. Thank you. Bye-bye.
Bye-bye.
Thank you very much.
Thank you.